Namaskar. Very warm welcome to all the viewers and learners in this live interaction of CIT NCERT. I am Renu Bhatt with you all, and you are watching us live on eVidya channel, channel number 8. And apart from these channels, you are with us on our YouTube channel as well, that is NCERT Official and NCERT PMeVIDYA class number 11. And in this specific session we are going to learn more about laws of motion part 2nd. And dear learners, we have already discussed about part 1st. If you want to know more about laws of motion, you can explore our YouTube channel for part 1st, and this session is for physics 11th standard students. And we all know about motion, what motion is, and motion is quite important thing for us. जब भी कोई ऑब्जेक्ट अपनी पोजीशन चेंज करता है तो मोशन कहलाया जाता है, और मोशन के लॉज के बारे में न्यूटन्स लॉज ऑफ मोशन आपको बताया गया पिछले सत्र में, पिछले सेशन की हम बात कर रहे हैं. आज हम और ज़्यादा जानने वाले हैं लॉज ऑफ मोशन के बारे में. वी हैव जॉइंड बाय आवर एक्सपर्ट, सो विदाउट एनी further delay, let's quickly meet him. You are Mr. I.K. Gogia. Gogia sir, आपका बहुत बहुत स्वागत है.
Namaskar, thank you.
And sir is formerly PGT Physics from Kendriya Vidyalaya Sangathan, New Delhi. Dear learners and viewers, in case you have any query, you want to know more about laws of motion, या फिर आप इस चैप्टर में कहीं पर अटक गए हैं, आप अपनी कोई बात हमसे शेयर करना चाहते हैं, you can reach out to us through our various mediums. We want you to call us on our telephone number, that is 8800 440 559. Either you can drop a mail as well. Our email address is dth.class11@cit.nic.in. And if you have joined us through our live streaming, that means you are on our YouTube channels, then you have to go to the live chat box, and then only you can drop your comment out there. Our expert will be more than happy to answer all your queries and doubts if you have any. And we want you to participate in this particular live interaction because we bring this session only for you. तो हम फटाफट शुरुआत करते हैं आज के इस सत्र की. And sir, like we have already told our learners, this is our part 2nd. We have already discussed about part 1st. So we would like you to start this session with a brief recap of part 1st, sir.
Sure. Dear viewers, when we study motion, we study it in two parts. One is kinematics and other is dynamics. Kinematics is the study of motion of objects without taking into consideration the factors which affect. Means we study the speed, the velocity, the initial velocity, final velocity, acceleration, distances and their correlation. But we don't go into the details of why motion is caused and what is speeding up or retarding the body or what is changing its direction. However, when we talk about the laws of motion, we also take into account the factors which cause a change in the state of rest or motion of the body along a straight path. Here by the term factors we mean the forces. Let's begin with a quick recap of the previous lecture. In the previous lecture we have studied about the inertia, that is the property of an object by which it opposes a change in its state of rest or uniform motion along a straight path. It implies that the body cannot come from rest to motion on its own, it cannot come from motion to rest on its own, it cannot change its direction, its speed will neither increase nor decrease. This is what is inertia. According to Newton's first law of motion, every object continues to be in its state of rest or of uniform motion along a straight line unless it is compelled by an external force to act otherwise. That is, for change in state of motion, force is an essential condition. Rather, unbalanced external force, we have talked about these terms in part 1. This law is also known as the law of inertia. There are three types of inertia: the inertia of rest, the inertia of motion and inertia of direction. There are numerous examples in daily life for the three different types of inertia. we studied an important concept related to motion of an object, the momentum. It is a measure of the quantity of motion contained in a body. The momentum is the product of mass of an object and its velocity. The momentum is a vector quantity and its direction is same as that of velocity. Since it is product of mass and velocity, the SI unit is kg meter per second. Second law of motion relates momentum with force, and we state it as the rate of change of momentum of a body is equal to the force applied on the body, and the change in momentum takes place in the direction of the applied force. Third law of motion: to every action there is always an equal and opposite reaction. That is, every action will essentially evoke a reaction. This implies that number of forces in nature will never be odd. It will always be even, because forces exist only in pairs. Action and reaction, although they are equal and opposite, but they do not cancel each other, because action acts on one object and reaction acts on a different objects. Hence, they do not cancel. Now, in this second part on laws of motion unit, we will be studying the principle of conservation of linear momentum, which is a very important fundamental law in physics, having wide ranging applications. You must understand this law very clearly, because you will have to apply this law in a number of situations in daily life, in your subject in class 11 as well as further study in class 12. Then we will talk about the types of forces in nature which we apply on the objects and which alter or affect the motion. We will talk about the friction, about which you already know. We will be discussing it in detail. Then we will discuss the types of friction and the relative values of the different types of friction. Then the friction is termed as a necessary evil, an interesting name. Two parts are there. It is a necessity, means there will be problems in case we do not have friction, and it is an evil because it poses problems in daily life. We will discuss all these things in detail in today's lecture. We begin with the principle of conservation of linear momentum. The second law and the third laws of motion, which you have already studied, lead us to this important fundamental law in physics. The law can be stated as, if there is no external force acting on a system, or alternately, there may be forces but the net effect is 0. In these two conditions, no external force on a system or the net force acting on the system is 0. These are the underlying conditions under which this law is valid. It states that if net external force acting on a system is 0, the total linear momentum of the system remains constant. Implies that if you need to change the momentum of the system, you need to apply an external unbalanced force on the system. Let us verify this law of conservation of linear momentum for an isolated object. From your knowledge in law of inertia, you can easily see that this law can be deduced for a single object. For an isolated object, the law of conservation of momentum follows from law of inertia. Let us take an object of mass m moving with velocity v. The momentum will be m into v, the product of mass and velocity. If no force is applied, that is if force is 0, the law of inertia implies that velocity remains constant. As mass of an object is also constant, the product m into v or the momentum of the body will remain constant. So, this implies that for a single isolated object, by isolated object we mean no external force is acting on the object, the product mass into velocity or the momentum remains constant, verifying this principle for a single object. Now, let us take a pair of objects, conservation of linear momentum for a pair of objects. Here we will consider two objects and prove that the law of conservation of momentum is valid for a system of two objects also. Let us term the bodies at body 1 and body 2. Suppose two bodies 1 and 2 collide. During collision, one will exert a force on body 2 and by third law of motion 2 will exert a force on body 1. Since the law of conservation of momentum is valid only for isolated systems, that is no external forces should be acting on the system. There may be mutual interaction as we have in this case. In collision, the bodies will exert forces on each other. Suppose body 1 exerts a force F21 on body 2. F21 means force on second object due to first object, and body 2 exerts a force F12 on body 1. So, F21 is force on 2 due to 1 and F12 is force on 1 due to body 1. By third law of motion, these forces are always equal and opposite. Either of the two forces can be termed action, the other force will become reaction. That is, we have F12 equal to minus of F21. This will imply the sum of the two forces, F12 plus F21 will be 0. There is a force acting on body 1 and a force acting on body 2, but for the system the total force happens to be 0. So, according to second law of motion, the force is equal to rate of change of momentum. When we apply this law to object 1, the force F12 here is equal to rate of change of momentum of object 1. Similarly, when we apply the second law to object B body 2, then force on 2 due to 1 is equal to rate of change of momentum of the body, second body, that is dP2 by dt. We studied earlier that action and reaction are equal and opposite. So, when these two forces are added, the net force happens to be 0. So, these equations imply that dP by dt of the total momentum of the system of two bodies P1 plus P2 is 0. That is, the rate of change of momentum of the system is 0. Body A has a non-zero rate of change of momentum, body B or body 2 also has a non-zero rate of change of momentum, but for the system the rate of change of momentum is 0, which implies that there is no change in momentum, or the sum P1 plus P2, the total momentum of system of two objects is constant, again subject to the condition that net external force acting on the system should be either 0 or there should be no external force acting on the system. So, we have been able to verify the law of conservation of momentum for a single isolated object and for a pair of objects. We can generalize it for n particle system now. For n particle system, the total linear momentum is given by P equal to P1 plus P2 and so on. You have to add momenta of different objects P1, P2, P3, P4. The total sum we have denoted here by letter P. Also by second law, we have rate of change of momentum, that is dP by dt equal to net external force. For net external force 0 as 0, which is the underlying condition for application of principle of conservation of linear momentum, we will get dP over dt equal to 0, which implies that the momentum of the system of n objects remain constant, or the total linear momentum of the system is conserved. So, this is a simple law, but it has wide ranging applications. Let us take an illustration of conservation of linear momentum. Here we have an object at rest. Since the object is at rest, velocity will be 0. For this stationary block, the initial momentum is 0. Suppose the block explodes into pieces as shown, look at the diagram. Explosion is a random process. We cannot predict the number of pieces it will break into. But here in this diagram, we have shown 5 pieces, 1, 2, 3, 4, 5 you can term, and their momenta are P1, P2, P3, P4 and P5 respectively. Remember, initial momentum of the system when it was a single block was 0. Then there is an explosion. Explosions, maybe this is a pataka going on its own, or maybe it's a bomb exploding into pieces. The total final momentum of the system will be P final equal to P1 vector plus P2 vector plus P3 vector up to P5 vector will be 0. To conserve momentum, sum of momenta of all the pieces must add up to 0. Since initial momentum was 0 and there is no external force, therefore, the final momentum of the system will also be 0. Another example, when a bullet is fired from a gun, we know that the bullet moves forward and the gun recoils. That is why the firing of gun is a technical job and you have to firmly hold the rifle on your shoulder, otherwise one may get hurt. This is a bullet and the gun system. Initially the system is at rest, therefore its initial momentum Pi is 0. We don't apply any external force for firing the bullet, we just press the trigger releases a spring, and it's the spring which is a integral part of the bullet gun system. It exerts a force on the bullet. So, the forces acting here are internal forces, we are not applying any external force. So, momentum in this case will be conserved. The bullet moves forward with a velocity v. Here small m denotes the mass of the bullet and small v denotes the forward velocity of the bullet. So, momentum acquired by the bullet in this case is m into v. The gun recoils and the momentum of the gun is given by capital M, the mass of the gun, multiplied by capital V, the velocity. Since the initial momentum was 0, by principle of momentum conservation, the final momentum also will be 0. So, you can write an equation mv small v plus capital M capital V equal to 0. Transposing, you will get capital V will have a negative sign with respect to small v, which shows that the gun will recoil. So, this is the equation we can write for final momentum. Pf is equal to mv plus m into capital V equal to 0.
So, sir, can you please tell us more, any other activity or more activity based on this law, sir, to all these students?
Yeah, sure. There are very simple obvious examples which the children can try and enjoy. Say A very simple case is, take the case of a balloon. Inflate the balloon, hold its opening. Since the mixture of gases filled in the balloon and the balloon, they are stationary, the momentum of the system is 0. Release the balloon and it moves in opposite direction to the mouth. The gases flow out in one particular direction, gaining momentum in one direction, and the balloon rushes in opposite direction. So, momentum acquired by the gases is equal to the momentum acquired by the balloon. The total momentum again in this case is 0. Jet planes also work on the same principle of conservation of linear momentum.
Okay. Yes, sir.
Now, about that bullet gun system, you can ask yourself and try to answer this question: why does the bullet move faster? Another question which you can think about is, why is the gun heavier as compared to the bullet? Try to think about these questions and try to find the answers. You can discuss with your friends and get to the answers by applying the principle of conservation of linear momentum. Now, let us come to the types of forces in nature which we can apply on different objects. We broadly classify forces into these categories. Contact forces, as the name suggests, these forces can be applied as a push or a pull involving a direct contact between the agent applying the force and the object on which the force is being applied. Some examples of contact forces are a horse pulling a cart. Until unless there is a contact between the horse and the horse cannot pull the cart from a distance. The contact may be through a rope or through some other physical means. A fielder catching a cricket ball, we always see that there is a direct contact between the cricket ball and the hands of the fielder. This is another example of the contact force. The force of friction. The friction acts only between two objects in contact when one object tends to or actually slides over the other object. Another example of contact forces, and we will be discussing about this force of friction in detail in today's lesson. Air resistance. You must have driven a bicycle in windy conditions, and there the wind or air is in contact with you and you can feel the air resistance. Another example of contact force is the viscous force. Honey is an example of a viscous fluid. Okay. Here different layers of honey, they offer resistance or friction to the flow of the neighboring layer. So, another example of the contact forces which retards or opposes the motion of one layer of a viscous liquid over the other layer. Another class of forces is the field forces. The field forces act between bodies from a distance. Some of the examples are gravitational force. You know that the moon moves around earth due to gravitational force. So, earth is exerting a force on moon from a distance without any actual contact between them. Likewise, the planets go around the sun due to gravitational force without any actual contact between the planets and the sun. Another example of field force is electrostatic force. We know that like charges repel and unlike charges attract each other from a distance. No direct contact between the objects is required. These are the electric or electrostatic fields of the two objects, two charged objects interacting with each other from a distance. Then another example is magnetic force. Magnet pulls an iron piece from a distance without contact, because the iron piece happens to be in the field of the magnet. Similarly, the like poles of two different magnets which will repel each other from a distance because of their fields interacting with each other. The field forces are thus examples where the forces act without contact or from a distance. Another category of forces is the restoring forces, an important class of forces. These forces originate from elasticity property of the bodies. Elasticity, you know, is the characteristic or property of a body by which it tries to regain its original shape and size once the external deforming forces are removed. Like you pull a spring, the moment you release the force, the spring tends to regain its original shape and size due to the restoring forces which are set up in the spring when in the rubber band or spring when you pulled it. Here in this diagram you can see a spring with a mass m hanging on it. The weight mg of the block elongates the spring. The spring exerts an equal upward force. The moment you release the mass, the spring will regain original shape and size. So, examples of restoring forces are tension in the strings, forces applied by compressed spring or elongated spring. When you pull or increase the length of a spring, you experience a backward or opposing force which tries to contract the spring. Similarly, if you compress it, your hands will be pushed apart by the elastic forces or restoring forces. Now, as we stated earlier, we have to study another important force which affects the motion of the objects in daily life, that is the force of friction. We will discuss this force in detail in today's lesson. Let us consider a body of mass m at rest on a horizontal table. Here is the object on a horizontal table. Mass of the object is m, the acceleration due to gravity is g. So, this block is being pulled downward by earth with a force mg, and therefore, the block exerts a force equal to its weight on the horizontal surface. This is the surface of the table, horizontal surface of the table, and a force mg acts downward. The tabletop will exert an equal opposite normal reaction n by third law of motion. So, the forces are the force of gravity mg, and this force is cancelled by normal reaction n of the table. Let us apply a small horizontal force F on the block from left. Remember, I am stressing the word small horizontal force, small enough so that the block does not move. Since the block is not moving, it means the net force on the block is 0. So, this force is obviously being balanced by an opposing equal force Fs, which is shown in the diagram. This force originates from friction between the block and the tabletop. So, this force is a contact force and is equal and opposite to the applied force. You can see the statement, the applied force F is balanced by an equal opposing force, that is the force of static friction Fs. Static here implies that the bodies are not moving, they are at rest. the force acts parallel to the surfaces of contact and opposite to the applied force. Let us increase the force F gradually, very slowly you increase the force F, so that the body still does not move. It means the net force in the body is still 0. Fs, the force of static friction, is still capable of balancing F. Our applied force capital F, remember, is not constant, we are gradually increasing it. It means the force of friction is also gradually increasing, and it is always equal and opposite to the force applied by us. So, friction in a way is a self adjusting force. Now, you can see that the body remains in equilibrium or it does not move because the force Fs caused by friction is increasing in magnitude to be always equal to capital F and able to balance it. That is, we can term friction as a self adjusting force, self adjusting because it is automatically by itself increasing its magnitude to be equal to the applied force F. However, if you keep on increasing the applied force, we will reach a stage where we will be able to push the block. It means the friction, the static friction, is no more capable of balancing the external applied force which is trying to move the block. Implies that Fs, the force of static friction, is a self adjusting force increasing in magnitude up to a certain maximum limit, beyond which it cannot increase its value in a particular situation. That is why the body will begin to slide on the surface. So, this maximum possible value of the static friction is denoted by Fms. We call it the maximum force of static friction. It is also termed as the force of limiting friction. Remember, maximum force of static friction. So, all other values of frictional force will be less than Fms. This is implied by the prefix maximum force. As stated, this is the maximum force of static friction. Now, let us reverse the direction of the applied force. We are now applying force from right side of the body. See here, the applied force has shifted from right. Now, we are trying to move the object from right to left. The force capital F, as in the earlier case, is still very small and the body does not move. We are all over beginning the same activity, changing the direction of the applied force. It means the frictional force now acts from left to right to balance the applied force. The property of force of friction, that is, it is a self adjusting force. It is not limited just to magnitude, and it also is automatic or self adjusting so far as its direction is concerned. The direction of the force of friction will always be opposite to the direction in which the body tends to move. When the body tends to move towards right, friction acts towards left. When the body tends to move towards left, the friction will act from left to right. It will always oppose the motion. So, about friction we have certain important points to remember. If you do not apply force, there is no static friction. The force of friction comes into play the moment there is an applied force. When you apply a force, your applied force will be opposed by friction. That is, I repeat, comes into play only when there is a force which tends to move the object. The force of static friction increases with increasing applied force. We have seen it in the activity which we discussed. it is equal and opposite to the applied force up to a certain limiting value Fms, which is called the maximum force of static friction, and up to the force Fms, if our force applied force F is equal to Fms, the body will remain at rest because the friction is capable of balancing the applied force. Static friction always opposes impending motion. We will explain the term impending motion. Experiments show that the limiting value of static friction is independent of area of contact. Now, this needs an slight elaboration and explanation. Let me take this book. If I keep the book on the tabletop, this is the area in contact. For the given weight, I will need a certain force, minimum force to move the block. That minimum applied force capital F is a measure of the maximum force of friction. Supposing I turn the book in this way, the area of contact with the table will change, it will reduce to this area, but the experimental measurements show that the force, maximum force of static friction still remains the same. I have a third option, keeping the book this way, the area is further reduced, but the force of maximum friction or the force of limiting friction still remains the same, justifying our statement that it is independent of area of contact, provided the weight of the object or the normal reaction remains the same. Here the term impending motion means the motion that would have taken place under the action of the applied force had there been no friction. But since friction is always there, we cannot eliminate, we can reduce friction. So, the motion here is not actually taking place because the body is stationary. So, impending motion, when we were applying force towards right, the impending motion was towards right, but friction is towards left, therefore, it opposes the impending motion and does not allow the body to move. Then we know that if we reverse the direction of applied force because of self adjusting nature of direction, the friction will again oppose the impending motion. The maximum force of static friction depends on nature of surfaces in contact. Rough surfaces, more friction, smooth surfaces, lesser friction. The maximum force of static friction is directly proportional to the normal reaction. Now, if we elaborate this, supposing I have shown you this book, for one book I measure the value of Fms, record it as Fm say n, then I keep another object on this, another identical book on this, the maximum force of static friction will double its value because the normal reaction is doubled, it is now equal to weight of two books, therefore, the maximum force of static friction will also become double. If I keep three books one over the other, the normal reaction will be tripled and the force of static friction, maximum force, will also be tripled, which shows that Fms is directly proportional to normal reaction n. Then to change it to an equation, I have to introduce a constant mu s, which is called the coefficient of static friction. The value of coefficient of static friction will depend on nature of surfaces in contact, and as I stated earlier, it is larger for rough surfaces and smaller for smooth surfaces. So, this is just a repetition to reinforce what you have studied earlier. Fms depends on nature of surfaces in contact. Remember, it is independent of area of contact provided the normal reaction is same. The maximum force of static friction is proportional to normal reaction, or it is equal to mu s n, where mu s is coefficient of static friction. So, here we have written an inequation f S, the force of static friction, is less than mu s n or equal to mu s n. Remember, the left hand side is not Fms, it is Fs, the force of static friction, which has a certain maximum value. That maximum value is Fms, which is equal to mu s n. So, right hand side indicates the maximum value of static friction, whereas left hand side has various values of static friction, where the body is trying to move, but not actually able to move, not even on the verge of moving. So, that is why Fs is less than or at most equal to mu s n, the maximum force of static friction. Now, if we apply a force F exceeding Fms, then we will have a net unbalanced force capital F minus Fms, then the body will begin to slide on the surface. When two bodies are in contact, each of the two bodies experiences a contact force by the other due to the force of friction. So, friction is thus the component of the contact force parallel to the surfaces in contact, which opposes the impending or actual relative motion between the two surfaces. This statement you must always keep in mind. Impending motion, you have static friction. Actual relative motion, we have a different type of friction, we call it sliding or kinetic friction or rolling friction, about which we will discuss in a minute. This is again important about inertia. It is not the motion, but the relative motion that the frictional force opposes. The frictional force does not oppose the motion, it opposes the relative motion between the two objects. We can illustrate and explain this. Let us consider a stationary box in a compartment of a train, and the train is accelerating. Box in a compartment in a train which is in accelerated motion. The box is stationary relative to the train and is accelerating along with the train, and since there is no relative motion between the box and the train, it means the acceleration of the box is equal to the acceleration of the train. Now, going to first law, if we apply first law of motion to the box and there is an acceleration, it means some force must be acting on the box to speed it up. The only conceivable force here along the horizontal is the force of friction between the box and the train. In absence of friction between the box and the train, the floor of the train would slip forward and the box will remain at rest due to inertia. So, it is the friction which is producing forward equal acceleration in the box. In absence of this force of friction, the box will not be accelerated, it will stay stationary, and therefore, it will hit the back side of the train, a funny situation which we know normally does not exist. This impending relative motion is opposed by the static friction Fs between the box and the floor of the compartment, and you can see it is a repetition. Static friction provides the same acceleration to the box as that of the train, keeping it stationary relative to the train. Now, let us take a few problems or examples in which we can apply the concepts which we have studied. One of first example which we are considering is determine the maximum acceleration of the train in which a box lying on its floor remains stationary, given that the coefficient of friction between the box and the train's floor is 0.15. For answer, let us see, since the acceleration of the box is due to static friction and we are looking for maximum acceleration, we have acceleration equal to the force of friction, static friction, multiplied by n, that is the maximum force of static friction we know as mu s n, and normal reaction is equal to the weight of the box, that is mg. So, the force, maximum force available is mu s mg. This force gives us the maximum acceleration by second law of motion. We have left hand side is mass into acceleration, the force on the box, and this is the maximum available force. So, here this will give you cancelling mass from the two sides of the equation. You get acceleration less than or equal to mu s, the coefficient of static friction, multiplied by acceleration due to gravity. So, this is maximum acceleration, 0.15 the coefficient of friction into 10 the acceleration due to gravity, that is the maximum probable acceleration of the train will be 1.5 meter per second square. In case train accelerates at a higher rate, then the block will hit the back side of the train. Another example, you have a mass of 4 kilogram resting on a horizontal plane. The inclination of plane is gradually increased until the mass just begins to slide. This diagram explains the condition which we are considering. You have to find the coefficient of static friction between the block and the surface. Please note the conditions given. Theta is the angle at which the plane OB is inclined and the box is about to slide down the plane. About to slide down the plane, recall the force of friction is maximum, FMS, the force of limiting friction or the maximum force of static friction. Now, let us see how can we get to the coefficient of static friction in this case. The forces acting on the block are the weight mg vertically downward. The forces are shown in the diagram. The normal force N of the plane on the block, this will be perpendicular to the surface OB in contact between the box and the inclined plane. Third is the static frictional force FMS opposing the impending motion. Here you can see from the diagram, the impending motion is down the plane. On its own the block will not slide up, the impending motion is down the plane. So, frictional force Fs is shown up the plane. Let me show you give you a very clear picture of the situation. This is an amplified version of the same diagram where the forces are very clear. Now, what we are going to do is we will resolve the forces to study the motion. Since the motion is possible down the plane or up the plane, we will resolve the given three forces along or perpendicular to the plane and see. This is the diagram for your reference. In equilibrium, the resultant of all the forces will be 0. Resolving weight mg along and normal to the inclined plane. The components are mg sin theta, which is balanced by the force of static friction. This gives you equation 1. Mg cos theta is balanced by normal reaction. This gives you equation 2. Now, Fs, the force of static friction, is equal to mg sin theta. Clearly, mg sin theta depends on sin theta, which depends on theta, which we are varying. Here, theta is such an angle where the body is about to slide down the plane. Therefore, the frictional force is maximum. So, in equation 1, you can replace Fs by Fms, the maximum force of static friction. The equations are reproduced for your convenience. Dividing equation 1 by 2, you get tangent theta, left hand side is mg cancels out, you get sin theta over cos theta, which means tangent theta, which is Fms. I repeat, the force of friction here, the maximum force Fms, and divided by normal reaction, its coefficient of friction. So, coefficient of friction is equal to tangent of the angle of inclination here. This special angle theta depends only on mu s and is independent of the mass of the block, which has cancelled in this equation. So, for lighter mass or heavier blocks, the value of tangent theta will always be equal to the coefficient of static friction. This angle has a special name, we call it angle of repose. Another type of friction is kinetic friction. As the name suggests, the moment the applied force exceeds the maximum force of static friction, we know that the body begins to slide. The friction is no more static, we call it kinetic or sliding friction, denoted by Fk. We are changing the suffix to from S to K, and Fk is less than Fms because Fms is maximum possible value of the force of friction. So, any other value, whether it is static or kinetic, will be less than Fms.
So, here let me tell you that we have 5 more minutes left for the session, sir.
Yeah, we'll wind up. Fk is found to be independent of area of contact and nearly independent of velocity. Experiments show that force of kinetic friction is less than maximum force of static friction. As an illustration, recall when you just start a bicycle. It's slightly difficult and requires more effort to start a bicycle. Once it starts moving, then the force required to maintain motion is less than the force which you initially had to apply to start the block. So, Fk, the force of kinetic friction, is less than the maximum force of static friction, giving you mu k less than mu s. The force of kinetic friction, like static friction, depends on nature of surfaces in contact, and the acceleration of the body can be calculated as applied force capital F minus the force of kinetic friction. That will give you the net force acting on the body divided by mass, that gives you the acceleration of the body when it is being accelerated by an external applied force capital F. Suppose the applied force happens to be equal to Fk. Then the body will move with constant velocity because net force is 0 and there will be no acceleration. If you remove the applied force, that is capital F will be 0, the acceleration will be negative due to friction minus Fk by m, till eventually the body comes to rest. Once the body comes to rest, friction will cease to act. We know no motion, no friction. Remember, the laws governing the force of friction are not fundamental laws, they are approximately true, they are empirical or experimental laws. Variation of force of friction with applied force. This graph shows the variation of force. In the first, this is along x axis we have applied force, along y axis we have the force of friction. Here, as long as the graph is straight line, the applied force and frictional force are equal, and the force of friction here is static friction till it attains a maximum value Fms. This peak shows Fms. The moment the applied force exceeds Fms, the body comes to motion and the force changes to kinetic friction, as is written here, kinetic or sliding friction. Then the required force slightly reduces, it is less than the maximum force of static friction, till ultimately the body attains, and the force of friction, the kinetic friction, attains a constant value shown by a line parallel to the x axis here. Another type of friction is the rolling friction. When one surface rolls over another, the force of friction is kinetic but not sliding, it changes to rolling friction and it is far less than the kinetic friction. We denote it by Fr. We have Fr less than Fk less than Fms.
Okay. So, this is rolling friction. Could you please explain this with some example or real examples, sir?
Yeah, it's very simple. We have a very simple illustration or activity by which we can actually show that the force of rolling friction is less than the force of sliding friction. Let's take the case of this book. I am trying to move this book, slide this book. I have to apply a certain force. Now supposing you can feel the effort that I am applying. Let me change this force to the friction to rolling friction. For this I have simple two identical pens. I will use these as rollers here.
Okay.
And now I am keeping the book on the pens, and see, I will apply a force, a slight force, and see how fast the book is moving, showing that the force of rolling friction is far less than the force of kinetic friction, and we already know that the force of kinetic friction is less than the force of maximum force of static friction.
So in a brief we would like to know, sir, because we are running very short of time, sir.
Yeah, we are about to wind up. So these equations you already have studied. The force of rolling friction depends only on surfaces of surfaces in contact. Remember, the laws which govern kinetic friction or rolling friction, they are very much the same like the laws of static friction. Here is a practical example. We make use of ball bearings to reduce the force of friction, because the ball bearings change rolling friction, change the kinetic friction to rolling friction, and the motion becomes easier. Friction is termed as a necessary evil. A necessity because we can walk only because of the force of friction. We cannot walk on a slippery surface because of absence of friction. A car doesn't move on a slippery road. Once the car or the machinery parts come in motion, the braking force brings it to rest because of the force of friction. Friction between tires and roads provide the road grip, otherwise the tires will slip and the car may meet an accident. Friction is an evil because it opposes motion, it causes wear and tear of the machinery parts and dissipates power, resulting in loss. Here are some methods by which you can increase friction or decrease the forces of friction. To increase friction, we make use of corrugated or rough surfaces. We create high friction spots in a matchbox and use sand to dry up muddy patches. Let's sum up what we have studied today. Principle of momentum conservation states that if net external force acting on a system is 0, the total linear momentum remains conserved. Friction is component of constant force parallel to the surfaces in contact, which opposes impending or actual relative motion between the surfaces. We have the rolling friction less than kinetic friction less than the maximum force of static friction. In the concluding part, we will study further applications of the frictional force.
Definitely, and that was indeed very informative session. Thank you so very much, Gogya sir, for being with us. Thank you for your precious time. Thank you. And I am quite sure this session would be beneficial for all the physics 11th standard students. You came to know a lot of things like laws of motion and frictions and rolling frictions and a lot of important other things. It's time for me to take a small break. लेकिन ब्रेक के बाद हम अपने एक और लाइव इंटरेक्शन के साथ हाजिर होंगे जो कि हिस्ट्री के यानी कि इतिहास के 12वीं कक्षा के विद्यार्थियों के लिए है और हमारा शीर्षक रहेगा विचारक, विश्वास और इमारतें। तो आप यूं ही हमारे साथ बने रहें eVidya चैनल एनसीईआरटी ऑफिशियल यूट्यूब चैनल के साथ साथ NCERT PM eVidya पर। मी रेणु भट्ट इज टेकिंग योर लीव। नमस्कार, टेक केयर।